Obviously my topic here is blind frequency hopping, spread spectrum signal separation with constrained clustering. So I'll go ahead and get started. So I'll talk a little bit about what frequency hopping spread spectrum signal actually is. So typically a modulation scheme of some kind, usually MFSK, is chosen, and instead of a signal being transmitted on the same frequency over time, it's actually hopped between frequencies. And this is, so sometimes, depending on the type of frequency hopping, whether it's fast hopping or slow hopping, the signal will stay at some frequency for a longer time or a shorter time, just depending on sort of how it's modulated. So why do people use frequency hopping? One thing, it's very good against multipath interference. Another thing is it's pretty resistant to narrowband interference because it's hopping among many frequencies. It isn't affected by one certain band or constant interference at some certain frequency. It can be used a lot by several different users in the same bandwidth. So it's in that sense, it's a form of sharing the same band. And some devices that actually use this are Bluetooth devices. So your phone, a laptop, actually uses this frequency hopping technique, and it's also in a Wi-Fi standard as well. There are some other devices like walkie-talkies. RC uses Bluetooth a lot, among other things like cordless phones. In military, it's used for its sort of lower probability of detection. So when you have your signal hopping between multiple frequencies, it's harder to pin down where that signal is and identify it. So again, here, why is this important? So why is the separation of these hopping signals important? So why does this problem matter? Commercially, so Bluetooth signals typically have they do have a defined specification where they need to operate in terms of bandwidth, how long they can stay in a certain or at a certain frequency, so their dwell time. So say if there's a consistent signal that is operating outside of this required spec, maybe you want to identify what that signal is and maybe try and locate it. Another commercial reason to sort of identify this hopping signal is to find and locate a consistent interferer with your signal of interest. So if there's a signal that's commonly interfering with another signal, maybe try and identify what that signal is. And from a military perspective, if there's maybe you want to see how many people are in an environment and identify that number. That's one reason as to why you want to see how many and separate these frequency hopping signals. If there's a jammer, maybe you can locate and sort of reduce this jamming's effect on your signal if you can identify this frequency hopper and where it's coming from. So some previous work in this area. So there's a few works that tackle this problem, most of which claim to be limited by the number of sources that it can detect relative to the number of receivers that it's using to detect these signals. So some of the other claims are that sort of arid parameter estimation limits how you can separate these signals, and this is actually one of the things that I'm tackling directly. Some other requirements that previous works are dependent on is that the hops happen at the same time. So what do I plan to contribute in this field or this problem? First I want to show how these signals can be separated and sort of what range of estimation error they can be successfully separated on. So the approach, to demonstrate also an approach to this problem, is introducing clustering with the addition of background knowledge. So background knowledge is something that can help the clustering algorithm in this sense. And I'll go into what that background knowledge actually is in a second. Another thing is determine the accuracy required to actually separate these signals, and then to identify which parameters of these signals or what properties are useful to actually separate them. So here's sort of the block diagram of the scenario. So we have multiple frequency hopping sources. They don't necessarily need to be frequency hopping. This sort of algorithm will work with any type of signal in an environment. It's just that my interest and the interest is to actually separate hopping signals. So currently there's assumed to just be one sort of listener, so there's no direction information at the moment. In this hop detection stage, so this is like a typical spectrogram, like a time frequency, sort of waterfall is what it's called. So you have one axis is frequency and one is time, so you can see all these little blips are actually a hopping signal and what it looks like. So from that stage, and where sort of I take over is this parameter estimation and constraint assignment, which I actually am assuming the parameter estimation is already done, and I just looked at ranges of this parameter estimation. And the constraint assignment is what actually helps out the algorithm that I'm using in actually separating these signals. And you can see the clustering algorithm that's basically what it does. It finds groups of similar parameters and groups them together. So a few of the parameters that I'm looking at, and this plot here is actually the sort of the parameter generation that I'm using. So this is just a mix of a bunch of frequency hoppers with a lot of different parameters. So what I'm looking at is bandwidth and also majority bandwidth. So those are two of the same, like very similar properties, but it's mostly just looking at the spectrum and seeing the differences in spectrum of hops. So another thing is dwell time, so how long that signal stays at that set frequency. Power is another parameter that could be used. It's going to depend on the environment mostly. If you have a lot of fading, that power might not be as useful in this scenario. There's a few other parameters that could be used. One being mod class. Hoppers take a few common mod classes, but if you want to do some processing on these hoppers, that's another sort of parameter that you could introduce into this. Some things that make the environment a little more complex, maybe a little bit more realistic. Signals can be bursty. They can show up whenever they want, and they can start and stop whenever they want. So say if it's like a packet that you're sending, that'll come at various times. So typically with clustering algorithms, you have to process the data in some way in order to sort of maximize your performance in that sense. So normalization is important for any approach in pretty much doing a lot of anything really. But for this problem specifically, the clustering is based on the distances between the parameters. So you have to normalize these parameters, or else you'll have one parameter vastly outweighing the other in terms of just magnitude. So normalization is definitely required for this problem. That's just one of the steps I've taken to sort of make sure the clustering algorithm is doing what I think it's doing. Dimensionality reduction is another area that I've looked into. For this scenario, since the parameter set is fairly small, dimensionality reduction has not shown to really help that much. So it's just one thing that I've sort of considered, but mostly not quite as useful with this small of parameter set. So here are some very common clustering algorithms that I've sort of looked at. So this is one I wanted to set up as sort of the baseline of performance with these parameters. So one, k-means. K-means in optics. So k-means is distance based, and means is actually, I'll get into how this k-means algorithm actually works here later. These are just a few other algorithms that I tested out without constraints, obviously, just using the parameter sets alone. And I found that k-means and dbScan work the best. But there's actually, the reason I chose k-means is because there was a algorithm developed that sort of modified k-means in a way to make it a little bit more intelligent. And I'll get into what that actually means. So this background knowledge is the additional information that I wanted to use to sort of help the clustering algorithms. So clustering algorithms typically just work on parameter sets of your data. So n dimensions of different types of parameters. Those are the values that these clustering algorithms will work on. But those algorithms do not take into account other information about your scenario that can't be expressed in the form of a parameter. So in this scenario, a couple of the constraints that I've looked at, or one of the constraints that I'm using, direction of arrival is listed here, but that's sort of future work. Anyways, if a signal overlaps in the time domain, then I'm assuming that it's most likely not from the same source. So if it's any overlap in time, I'm assuming these signals cannot be grouped together at all. So that's where this COP k-means algorithm comes from. And I'm assuming this COP stands for constrained on parameters. So this COP applies constraints in the form of must link or cannot link during the point assignment stage. And so that's where it differentiates itself from typical k-means. One of the things about this algorithm, though, is that you can actually have some points that cannot be assigned, because if you have constraints with this point and with every other cluster in this scenario, you have to balance assigning this point to a cluster or violating a constraint. And I'll get into it again. I'll explain this a little better in these next couple slides. So here's sort of a scenario to just try and demonstrate what this algorithm actually does. So the first step so this data here is expressed in 2 dimensions. This data can have as many dimensions as you have parameters to cluster on. So I'm clustering currently on, say, 4 parameters. So this data would be 4 dimensions in my case, but you can't really express that visually. So this scenario, there's 2 dimensions, so 2 parameters that this sort of data is being clustered on. So the first step is to randomly initialize the centroids. So typically this is done by just choosing a point and saying that is where a centroid is. And the centroid is basically the cluster. It's the cluster mean, and it is the sort of the integer value of the number of groups that are in this scenario. So there's multiple methods of actually assigning these centroids. Currently I've just chosen randomizing. You can actually assign them with the help of constraints. You can assign them to where they're maximally separated distance-wise, but currently I'm just using a random initialization. So the next part of this clustering algorithm is actually drawing decision regions. So for k-means, typically you're just assigning the points that are closest to the centroids, assigning those points to that cluster, and this will sort of show where the constraints actually take place. So the next step is draw decision regions. So the third is actually assigning points based on these decision regions. So k-means, this red line here is actually expressed as a cannot link constraint. So these 2 points connected by the red line are points that cannot be linked in the same cluster. So as you can see here, this red point here on this above this line is actually closer to this centroid. However, given that constraint, it is assigned to the next closest centroid, which in this case is the red. So the next stage of this k-means algorithm is actually reassigning means. So now you calculate the means of those points you just assigned and readjust where these centroids are located, and then go back to step 2, redraw the decision regions, and then reassign points to the closest centroid or cluster mean. And one thing about these constraints is they can actually shift your centroids in the direction you want to sort of help out your clustering algorithm. So that was one constraint, right? This is a pretty simple scenario. So as you have more constraints on your parameters, this algorithm gets a little more complicated. So you run into some issues. So if you have points that violate a constraint with every other cluster, then that point cannot be assigned to any cluster in that scenario. So that's one of the sort of issues that this algorithm has. Also, in terms of how to measure how well the algorithm is doing, you have to consider those number of points that are not assigned, as well as just the variance of the clusters. So that's one sort of metric of measuring how well your clustering algorithm is working, is looking at the variance of the points of that clustering algorithm. So to analyze this in my scenario, I used I mostly used two main metrics. So there's normalized mutual information as the quality of the clustering algorithm, and I also swept this across this parameter estimation error. So this parameter estimation error is what I'm assuming the error is on the estimated parameters, obviously. The way I did this was add a sort of a Gaussian error to each of the parameters as being estimated, just to represent different qualities of receivers, among other things. Normalized mutual information is, the best way to describe it is, it's the reduction of uncertainty of the actual labels when you're given the clustering algorithm's guessed labels. So in terms of the clustering algorithm and actually assigning points, like what does that actually mean? That's one of the difficulties of this clustering problem, is actually to give a understandable representation of how well it's doing. But from a sort of performance standpoint, this is what is commonly used, so this is just what I chose to express that performance. So this again is the estimation error that I've used across my parameter set. So actually I'm using something called the coefficient of variation, and basically what this does is make sure that the estimation error is consistent across parameters. So it's usually expressed as a percentage, but it's a way to sort of keep your estimation error consistent across both your dwell time and your bandwidth and among the other parameters. So here's the first sort of performance analysis that I have and looking at. So the k-means algorithm's performance is expressed in blue, and the constrained algorithm is expressed in the orange. So the normalized mutual information is the y-axis here, and the estimation error is the x-axis. So this estimation error is consistent across all parameters, so it's sort of just uniform error across all parameters, and it basically, as this estimation error increases, it just means that your receivers are not doing as good a job of estimating these parameters. So normalized mutual information is again the reduction of uncertainty of your true labels from your clustered labels, and basically that measure is good. So the higher that is, the more I know about the truth labels given these clustered labels. So the higher the normalized mutual information is, the better it's doing. So in this case, the COP k-means is doing better than the typical k-means algorithm. And as you can see, as the estimation error increases, it sort of keeps a constant performance increase. So this test, this next plot is based on the sort of test points, and so the training points are what I actually use to find those cluster centroids. So the train points are what is used to sort of find the centers of where the clusters typically are, and the test points are actually what I've used to. So given those centroids are in their locations, I've just basically left out points in terms of I've left out points and then reassigned those based on those centroid locations that were found with the training points. So basically what this shows is that the COP k-means performs better when they're even after points are left out in terms of the centroid assignment stage, if that makes sense.
One question.
Yeah.
Why the red line increase a little bit at the initial stage, like when the estimation error?
Yeah, this little increase here.
Yeah.
That's a good question. I'm gonna contribute that to sort of just the Monte Carlo analysis and say I didn't have enough trials, and I would say that is sort of for all these sort of bumps.
Should I go in smoothly, like going
Yeah, yeah. Given more trials,
Yeah.
it would smooth out. I would assume. Yeah. But as you can see, like compared to the training performance, it is the difference is kind of similar. I mean, the advantages of I mean, the reason I'm looking at this test case is because it requires a little less computation if you can assign the centroids previously, which was in the training set, and then just from some point on in time, you can say, okay, after like a tenth of a second, you know where your cluster centers are, and you can just assign the points from there on out, and you don't have to do these recalculations of the centroid locations. So that's the basis of why this test set was used. So what does that performance actually mean? So this is my attempt at showing you what exactly the difference is in the parameter estimation error based on the difference in those that normalized mutual information. So basically, with the k-means algorithm, for the same performance, the k-means algorithm, I need a distribution on my parameter set that is this versus for the constrained k-means, I can have a distribution that's more similar to this. And this is for all parameters. In this case, I just chose power as a parameter, but this sort of spread and distribution is consistent across all parameters. So basically, this is just showing that I need more accurate estimation with the typical k-means algorithm versus implying constraints that I have much more tolerant to errors in your parameter estimation, and you can sort of see that. And this 3 and 9 is what the estimation error actually is. And if we go back to here, you can see that the separation between these two lines is about 5 or 6 in terms of this estimation error for some given performance. So this plot is showing a reduction in train points and the performance of the test case scenario. So basically what this is saying if I reduce how many hoppers or how many signals I have to train on, so basically if I reduce my observation window, how well do these algorithms perform with that reduction in window? And you can see here that as the points with less points, this k-means actually separates itself a little more. So it actually helps find those centroids better as the versus the typical k-means algorithm. So one of the things I told you is sort of a flaw of this constrained algorithm is the fact that you can have points that don't actually get assigned. So this is what I'm using to show that to show you how how increasing your estimation error of your parameter set, how that attributes to your points that you actually cannot end up assigning due to these sort of hard constraints. So you can see as the estimation error increases, this y-axis is the percent unassigned points. So for some observation time, I have some number of hops, and basically this is just the percent of hops that end up not being able to be assigned. So looking at 1 to 2% is actually not too bad in this scenario. Like looking at your 1 or 2% of hops to not being able to be assigned is really not the worst thing. But there's a few things you can do in terms of actually looking at these or dealing with these unassigned points. One thing I've looked at is actually just force assigning these points to the closest cluster centroid if they violate all constraints. So it's sort of a default to what k-means already does. So that's one way of handling this. These two lines here are both a constrained algorithm. The blue is the algorithm. So again, when you're looking at this constrained algorithm, you can sort of measure it in two different ways that I've thought of anyways. And one of those is getting the best result in terms of the number of points assigned. So say if you want, in your scenario, you want to have all your points assigned to some cluster, then okay, that's what you want. So that this blue line represents that case scenario. So you can see the percent unassigned points. This is the minimum that I can do with some iteration of this algorithm in terms of assigning points. And the orange line in this plot is the best I can do in terms of inertia. So inertia in the clustering algorithm world is basically just your variance of your clusters. So in this scenario, I say, I don't care how many points I don't assign, I just want to have the minimum variance for every cluster. So you can see this is kind of the separation between the two in terms of the unassigned points. And again, this is another sort of metric of showing how the unassigned points show up in terms of your actual number of constraints. So if I drop a number of sort of random constraints, this is how the unassigned points change. So 0 here means that I'm using every constraint, which again is the constraint is actually if the hoppers are overlapping in time. That is the constraint I'm enforcing. So if I don't drop any constraints, this is the sort of right side here is the number of points assigned, and I took it down to about 70%. So if I drop 70% off, this is the number of unassigned points that corresponds to that. And I looked at performance as well in terms of these the percent constraint drops, and I didn't see large fluctuations, which means it seems like I could actually use less constraints and get similar performance in that case. And here is inertia, which is, I guess I explained it before I got to it, but inertia is the, again, like sort of the variance of your cluster points to their centroids, or it's the measure of average distance to the cluster centroids for every point. So this is kind of interesting because it shows what k-means is meant to do. So k-means, the entire goal of k-means is to provide, like, put centroids at the most clustered data. And so k-means naturally minimizes this average distance to its points. So when you include constraints on this, you actually are increasing the variance of your clusters just due to the fact that you have points that are farther, like assigned to that cluster that are farther away, just because those constraints are being implied. So overall, what I found with this constraint algorithm, you can tolerate more estimation error in terms of your parameters when you include these constraints. Also, that the constraint-based algorithm requires less data to sort of find those initial centroids, and from then on you could basically just assign points to wherever that closest centroid is for your test set that I was showing. Future work, there is one sort of caveat to this COP k-means algorithm, and that is that your constraints are assumed to be perfect. So in the case of assigning constraints based on points overlapping in time, you're assuming that those points absolutely cannot be in the same cluster. But if you have errors on your timing estimates, which you naturally are going to have, these constraints might be in error, and then so now your hard constraints are no longer helping your algorithm, or at least they might not be. So sort of the next step is actually incorporate soft constraints, which means you sort of balance the distance from a point to its centroid, as well as the violation of a constraint. So now it's not, I absolutely cannot assign these points to, I can't assign these points with some penalty. Another thing here is with k-means, another issue with k-means is actually determining the number of clusters that there should be in a scenario. So that's sort of what the k stands for in k-means, is actually the number of clusters that should be in this scenario. So there's several methods, and people have been doing this for a long time, and so there's plenty of methods to actually determine this number of k. But one thing I want to look at is actually how the constraint, like the parameter or the constraints, impact this process, and seeing if they actually can help this determination of the number of k that should be in this point set. So another thing I wanted to look at is incorporating multiple constraints and maybe weighting these constraints based on the constraint accuracy. So if your timing estimates are not very good, but you can have very precise direction of arrival estimates, then your constraint with direction of arrival could be weighted more than your timing estimate constraint. And also, another thing to look at is exploring the differences in receiver properties. So some receivers might be better at estimating some parameters versus others, so actually weighting parameters based on their estimated accuracy rather than having just uniform estimation accuracy among every receiver in a sense. So that's sort of another thing to look at. And that's all I have. Are there any questions?
So I noticed when you first introduced K-means algorithms, there are some other algorithms for clustering.
Mm-hmm.
Could you use the slides? Yeah. So, did you have any chance to, use the background information for some other clustering algorithm? Except K-means.
Yeah, and that's a good question, and that there are, so spectral clustering is kind of like K-means. It just does a little pre-processing, and there's actually work been done that has used constraints with spectral clustering. It's just, I sort of saw this, so dbScan, I'm not actually sure if it's been done. I'm not sure if constraints have been used on dbScan algorithm. I chose K-means because it was just performing as well as everything else or better. But surely if dbScan could be used for constraint-based clustering, that would be great, because dbScan doesn't require your to know the number of k. Like, it doesn't need to know how many clusters there should be in your like point set,
yeah.
Which is better than having some estimate of k, most likely. So that's definitely, a place to look at potentially.
Yeah, maybe you can also do some comparison between all those clustering algorithms. When using background information.
Yeah. It could be, but another reason why I sort of chose K-means in that sense is because I knew that the constraints that I was going to be applying were not going to be perfectly accurate. So that's it's called hard constraints in that sense, is where you're assuming your constraints are perfectly accurate. So K-means there's already, so somebody already created an algorithm that implies the constraints, and there's an iteration sort of that does solve constraints. So basically there's just already sort of an avenue to go down in terms of which algorithm to use. So I'm not sure if, first of all, I'm not sure if dbScan would potentially use constraints in the first place, but implying those hard constraints might be, or the soft constraints might be a little more difficult with that algorithm. But it surely is interesting, and could maybe lead to some interesting results, that's for sure.
Any other questions?
How are you determining K? Are you just assuming that you don't know how many operators there are?
Yeah, so that's, before this goes in any kind of conference paper, that has to be handled. It absolutely has to be. For this scenario, one of the interesting things is actually determining the number of hoppers that are in a scenario. If you already know that number, then what's the point? There's which maybe you know this or not, but there's a method called the elbow method, which actually looks at the inertia. It sort of sweeps the number of k and looks at the variance of the points to the cluster centers. And basically, the idea is once you surpass your correct number of k, you're sort of splitting up like subclusters, and you don't really see a difference in the variance as much. So it sort of creates like an elbow in terms of your variance over your number of k, and sort of that elbow is where it's selected. So that's what I've looked into, and that's probably what I'm going to implement. But in the next very short amount of time, that's sort of where I'm